Hey everyone, my name is Aditya K. Kamath. Today I'm presenting pod attention, unlocking full prefill decode overlap for faster LLM inference. Before we get started, I'd like to go over what we'll be covering. We start off with a background on LLM inference covering prefill decode and hybrid batching, followed by a motivation for pod attention. We'll then look at how GPU execution and kernel fusion works, and this is followed by pod attention's design before finishing off with evaluation. Large language models, or LLMs, are extremely popular today. The fundamental unit of LLM architecture is the transformer block, which consists of self-attention and the feed-forward network. This block, repeating n times, makes up a large language model. When a user submits a prompt, the LLM processes it to produce the first token. This is called prefill. The time that this takes is called the time to first token, which is an important latency metric that modern LLM serving systems try to optimize. After the first iteration, the output is passed back into the LLM to generate the next token, which is called the decode. It is characterized by its relatively smaller input and output sizes. This process of passing new tokens back to the LLM continues until it stops generating tokens for the request. The time between two decodes is called the time between tokens, or TBT, which is another important latency metric that serving systems optimize for. Hybrid batching has emerged as the state of the art method of balancing these latencies. In hybrid batching, multiple requests prefill and decode are combined and operated on by the same model weights. This improves overall throughput by reusing model weights and reduces latency. When we take a closer look at how hybrid batching is implemented in frameworks, we see that the reuse of model weights does indeed happen for operations like pre-projection. Unfortunately, for attention operations, each input is operated on by a separate data item called a KV cache, which isn't shared across requests. GPU attention kernels are independently optimized for either prefilled large size or decode small size. This means that the inputs are separated and the attention for each is performed independently, following which they are again recombined for the rest of the LLM layer. Our work tries to reduce the overhead of the attention operations to improve overall LLM serving performance. Our motivation lies in the fact that for larger context lengths or number of input tokens, the attention operations end up being the biggest bottleneck, taking up to 60% of the execution time, as shown here. As context lengths are ever increasing, this problem will only increase in magnitude. And for the rest of this talk, we'll only focus on attention. We now look at the opportunities present for improving this situation. We profile the prefill and decode attention kernels to identify the compute and memory bandwidth utilization, which is shown in the y-axis. As the prefill attention operates on a large number of tokens seen in the x-axis, the prefill attention kernels are optimized for large matrix multiplications, which are largely compute bound. For decode attention, typically 10 to 100 requests are batched together and operated on, which have a small number of tokens compared to prefill. The decode kernels are optimized for smaller matrix multiplications, which are memory bound. We noticed that the utilization of memory bandwidth for prefill was below 5% and compute for decode was below 10%, which is quite low. From this we ask, is it possible to saturate both the compute and memory bandwidth together by performing these operations together? To answer this question, we must first look at how GPU processes operations. When a programmer launches a GPU kernel, they specify groups of 100 to 1,000 threads called cooperative thread arrays, or CTAs. The work to be done by the kernel is split among these different CTAs. For example, in tiled matrix multiplication, each CTA can handle a different matrix tile. These CTAs wait in a stream queue until a CTA scheduler assigns them to the streaming multiprocessors, or SMs, within the GPU where execution occurs. The SM is analogous to a CPU multiprocessor. In modern GPUs, each SM holds around 1 to 8 CTAs, and for the attention kernels we analyzed, each SM had up to 2 CTAs. Inside the SM, these CTAs are divided into warps, which are groups of 32 threads which execute in lockstep. In the figure, we look at the warps of a decode kernel which are memory bound, depicted with an orange color. A warp scheduler assigns queued warps to free resources every clock cycle. If possible, it attempts to saturate all the available resources. For the decode attention shown, these warps are all reliant on the load store unit to perform memory access. As all the warps are contending for the same resource, the warp scheduler has limited opportunity to overlap execution between the warps. Conversely, prefill warps are compute bound and contend for the compute cores. If instead we had prefill warps co-located with these decode warps within the same SM, the warp scheduler could attempt to service them all in parallel as depicted, thus improving overall throughput. Thus, to achieve the best performance and reach our goal of overlapping compute-heavy prefill with memory bandwidth-heavy decode, we establish a new sub-goal of co-locating the prefill and decode CTAs within the same SM so that the warp scheduler can overlap them. For this, we go over existing methods of kernel fusion and find that they all have limitations. Naive fusion and kernel parallel cannot guarantee operation co-location within an SM, as we shall see shortly why. Warp parallel execution exhibits bad load balancing within the GPU, and intra-thread fusion requires excessive synchronization overheads, which are required for correctness. The traditional method of kernel fusion involves combining the two kernels into one kernel, assigning the different CTAs to different operations. In the figure, the green CTAs perform prefill and the orange perform decode. The problem with this approach is that the CTA scheduler is handled by hardware, so there's no control over which CTAs get scheduled on which SMs, greatly limiting the speedup. Kernel parallel execution suffers from the exact same problem for the exact same reason. So we see that a major problem of fusion is that the assignment of CTAs to GPU SMs is hidden from the programmer as it is handled by the GPU driver in hardware. And so, to address this, we propose pod attention, which efficiently combines prefill and decode operations into a single kernel while guaranteeing SM-level co-location. Pod attention uses SM-aware CTA scheduling to guarantee co-location of prefill and decode within each SM. This allows the warp scheduler to overlap the operations and properly utilize both the compute and memory bandwidth of the GPU. Unlike other approaches, we can guarantee SM-level co-location as well as good load balancing. Previously, we would launch two kernels, one for prefill and one for decode, each with a certain number of CTAs depending on the inputs. With pod attention, we instead have a new kernel which is launched with enough CTAs for both prefill and decode combined. Instead of having a dedicated prefill and decode CTAs, we treat all of the CTAs the same before execution begins. Inside the kernel, we maintain three global variables shared by all the CTAs, namely SM counter array, the prefill counter, and the decode counter. The SM counter array keeps track of how many CTAs have launched on each SM so far. In the figure, we see that the counter array has 2, 1, and 2, which means 2 CTAs have run on SM0, 1 on SM1, and 2 on SM2. The prefill and decode counters keep track of how many CTAs have executed prefill and decode respectively. In the figure, we see that the prefill counter maintains 3, which indicates 3 prefills have executed, while the decode counter has 2, matching the 2 decode CTAs. We shall now look at how these allow us to co-locate prefill and decode operations, despite having no control over the hardware CTA scheduler. Once a CTA is launched by the CTA scheduler onto an SM, it first determines the SM it was launched onto by reading the SM ID hardware register, contained within each SM. In the shown case, the newly launched CTA reads the SM ID 1. It then increments the SM counter array for the respective SM, getting the value 1 from the counter array and replacing it with a value of 2. This informs the CTA that it is the second CTA to launch on that SM with an ID value of 1. We now apply a policy to decide what operation this newly launched CTA should run based on this value. For example, even-numbered CTAs can perform prefill, while odd-numbered CTAs perform decode. In the shown case, since it has a value of 1, it performs decode. The CTA then atomically increments the operator counter and executes it. This allows us to ensure that we don't run more operations than necessary. For example, if we only want 4 decode CTAs and the counter has a value of 4, we can perform prefill instead. Since each CTA determines its operations based on previously launched CTAs within each SM, we guarantee co-location of the different operation. And since each SM can hold 2 CTAs, load balancing is not an issue, since completion of one operation allows another to get scheduled on the SM. Our paper covers various optimizations that we perform to minimize interference between prefill and decode. For example, we use smaller decode tiles to minimize decode CTA compute utilization. We vary the number of CTAs per SM to allow more fine-grained overlap, and we reduce prefill splitting, which reduces the bandwidth pressure caused by prefill CTAs. To investigate pod attention's performance, we ran the attention kernel sweeping over 1,000 practical input configurations, varying the input sizes and LLM model configuration. We compare against state-of-the-art flash attention as well as flash infer kernels, and FA serial, our baseline, executes the two operations in serial, similar to how existing hybrid batch frameworks run these kernels. Streams executes prefill and decode in separate CUDA streams, which provides some limited speedup as early completion of prefill operations allows decode to start utilizing the GPU. Batched combines both prefill and decode inputs and runs a single prefill kernel. This ends up performing worse, as kernel execution is optimized for one set of inputs, which in this case is prefill, and adding other inputs leads to subpar execution choices like excessively large matrix multiplication tile sizes. HFuse is a state-of-the-art GPU kernel fusion tool that merges the warps of different kernel CPAs. Finally, pod attention outperforms all of these alternatives, performing up to 33% better on average with a speedup of up to 61%. We also evaluate pod attention's benefit on end-to-end LLM execution. We compare against state-of-the-art schedulers Vellum and Sarathi. Vellum uses prefill prioritizing scheduling, which stalls ongoing decodes whenever new prefill request arrives. Sarathi instead uses hybrid batching, which combines prefills and decodes into a batch to avoid these stalls. Finally, we look at Sarathi enhanced by pod to overlap the prefill and decode attention. We evaluate on a few different models on A100 GPU. Vellum prioritizes prefills, providing low TTFT at the expense of high TBT. Sarathi's hybrid batching suffers from high TTFT latencies as prefills and decodes are combined in a batch, causing the decode's attention latency to have an impact on TTFT. Pod allows both to overlap, achieving an acceptable latency in comparison. Our code is completely open source on GitHub and has been integrated into mainline Flash Infer. Thank you.